Good morning, afternoon, or evening, everybody. Hopefully you can all hear me okay. Welcome to the Sar Data in Python Get to Know the Asf Search Module Earth Data webinar. This is your host, Jennifer Brennan. It is 2 p.m. Eastern Time, so we're going to go ahead and get started here. What I'd like to do first is begin today's webinar with a few webinar logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or questions, please enter those into the Q&A panel rather than the chat located on the right side of your screen. Today's webinar is being recorded. The recording will be posted to the NASA Earth Data website as well as to our NASA Earth Data YouTube channel within a week of completion. Once completed, what I will do is I will send an email to all registrants that will include links to the recording as well as links to this afternoon's presentation and Jupyter notebooks. As far as timing is concerned, today's webinar will be 1 hour long with 45 minutes allocated to the presentation and demonstrations and an additional 15 minutes for the question and answer period. Our speaker for today's webinar is Gregory Short. Gregory is a senior software engineer at NASA's Alaska Satellite Facility Distributed Active Archive Center, or ASF DAAC. And what I'd like to do now is pull up this afternoon's agenda really quickly here. Okay. All right, so Gregory will begin today's presentation with a brief introduction and overview of the ASF DAAC and the Asf Search Python module. From there, he will transition to a series of Jupyter Notebook demonstrations and will show participants how to conduct a geographic search, Granule and product searches. He'll introduce a baseline search and also show you how to download data using the Asf Search Python library. Once our speaker is finished with this presentation and demonstrations, we will transition to an optional final set of polling questions. I will give these questions approximately 5 minutes or so before transitioning to the Q&A session, but I will leave the questions open much longer for those of you who would like to provide feedback. And then from there, we'll move directly to the Q&A. Depending upon the volume of questions that are received today, we will extend the Q&A period an additional 15 minutes from end time for those of you who wish to stay on the line, but with a hard cutoff of 3:15 p.m. Eastern. Excuse me, just a quick note about the Q&A period. We'll try to answer as many questions as possible within the time allotted, but if we are not able to address your question during the question and answer period, our speaker will follow up with you offline. With that, it is my pleasure to introduce today's speaker, Greg Short. Greg? Okay, I can see it. Thank you.
Great. All right. Thank you, Jennifer. And thank you, everyone, for being here. As Jennifer said, my name is Greg Short. I'm a senior software engineer at the Alaska Satellite Facility. For anyone that's not familiar with the Alaska Satellite Facility, we are a part of the Geophysical Institute of the University of Alaska Fairbanks. We downlink, process, archive, and distribute remote sensing data to scientific users around the world, such as yourselves. In addition to that, one of our components is the Distributed Active Archive Center, the DAAC, and we operate the NASA archive of synthetic aperture radar data from a variety of satellites and aircraft. If you're following along on the notebooks at home, there are a couple links you can explore here. One of these takes you to the ASF website. Lots of good information there and avenues to tools and services we provide. And there's also a contact link you can reach out to our support staff and ask any questions you have there. Drilling down a little further, the ASF Discovery Team. Our team's focus is to provide tools that help users find and acquire the data they want as quickly and as smoothly as possible. If you've worked with the ASF archive in the past, you may have used a few of our tools. First and foremost among them being Vertex. It's a web application for searching the ASF archive, as well as performing some forms of meta-analysis and custom on-demand processing. In addition to that, we offer the Search API. This is a public REST API for searching the ASF archive. And now within the last few months, we've added the ASF Search Python search module. This is a module for programmatically finding data and acquiring that data from the ASF archive. And that's what we're going to be talking about today. So working in Python, ASF Search, this is, as I said, a Python module made to simplify the process of finding data. What we found was that the Search API was very technical, and we saw a need to reduce that overhead required when using our Search API. And we saw that Vertex was very interactive. It's a web application. And so sometimes we need more automated or semi-automated processes. So we wanted to bring some of the power of Vertex into a simple to use programmatic interface. And lastly, downloading data can sometimes be difficult. There are a lot of ways to acquire data, and knowing how to use those tools can be complicated. So enter Asf Search. Today we'll explore some of the basic usage of Asf Search with a strong focus on the search functionality. A few features that we will cover include classes for working with Asf data, some of the search functions that are provided, and then authentication methods and, thanks to the authentication methods, download functionality. So this session is targeted largely at users who have a passing familiarity with Python. Asf Search is designed to be used easily by everyone, from novice to expert. So let's dive into it. And again, if you're following along at home with the notebooks, I think Jennifer's posting this link to chat occasionally. You can head over to our GitHub repo and take a look in the examples directory, and these are the 6 notebooks we will be going through today. Okay, so let's take a look at Asf Search. So Asf Search provides several helpful classes and functions to simplify working with our catalog. We're going to take a look at a few of those and how to get started with Asf Search initially. So before you start, we assume that Asf Search is available on your system. It's available through PyPy, Conda. You can grab the source from GitHub. It is all open source and freely available. And full documentation is available for Asf Search and a lot of other services offered by ASF at docs.asf.alaska.edu. And if we open those, you can see we have a number of sections and tools from Vertex to our cloud processing service Hype to Asf Search and our public REST API, the Search API. So assuming that's available, we did that through just a standard pip install Asf Search, and Asf Search requires Python 3.6 or higher. So usage. Once you have Asf Search installed, you simply import it as you would any other Python module. I like to rename it as ASF just for convenience, and we can run that. ASF version number is currently 306, so you can check that you're using the most recent version there. So performing a basic search. For this example, we'll specify 2 search parameters, a platform and how many results we want to retrieve. So we're going to start by looking at Sentinel-1 data, and we won't specify Sentinel-1A or B. We'll just say all of Sentinel. And we're going to grab the first 5 results that we find, just to keep this short. So to do that, we simply say results, and we say asf.search. We use platform equals asf.platform.sentinel1, and max results equals 5. Now, it may be useful. So this is actually run now in the background. We'll take a look at the results in a moment. It may be useful to handle your search arguments as a dictionary for moving them around and passing them between functions. So in that case, we support, you can use the keyword args functionality of Python to use that approach. So here I'm just storing them in this ops argument. Platform is asf.platform.sentinel1, and again, max results is 5, and we can just pass that dictionary directly in. Now you did note that maybe that I have this asf.platform.sentinel1 a couple times. We provide a number of constants, and as many editors support auto-completion using those constants. And this is just to kind of ease things. Maybe you can't remember if it's supposed to be a dash or an underscore or nothing, just to make sure you get the right values in your search parameters. And so we provide constants right now for beam mode, flight direction, instrument, platform, polarization, and product type. And you can explore those through whatever editor you like. PyCharm in particular works extremely well with these. So working with results. And this next section, if you are a complete Python novice, this might not be as exciting to you, or your eyes may glass over. That's okay. This is just to kind of give a framework for how we approach working with search results. So you may want to space out for 30 seconds if this is too technical. So working with search results, we provide a couple of classes, in particular the ASF search results class. Search results are all returned as one of these objects, and it is a subclass of user list containing a list of ASF product objects. Each of these classes, both ASF product and ASF search results, provide some additional functionality to help with working with those results and the individual products. So let's take a look at our previous results, our search for Sentinel-1 and the first 5 results. And you can see it is indeed just an ASF search results object with a list of ASF products. A closer look at ASF product. This class provides a number of metadata fields, such as geographic coordinates, latitude, longitude, the type of shape it is. In general, ASF data is going to be a polygon type. And then some scene and product metadata, such as path, frame, the platform, beam, polarization. Also, info about the specific product, the files. So we have file name, the file size, and the actual URL it can be accessed at, and a number of other metadata fields. So we'll take a look at those real quick. Here I'm taking a look at the first result in my result set from before. And I can just look at the geometry object. You can see I have the all the latitude and longitude corner coordinates and the type of shape it is. And then we can take a look at some of the other metadata that's available about the product. Here we have, this doesn't fit too well on the screen, but here we have a number of metadata fields. I mentioned a few of those. In particular, here's the file name, a browse image URL, the actual URL you can access the file at, and so on. And the particular metadata available in here is going to be growing in the future. So outputting this into something useful, the layout of those data structures, if you have worked with our search API in the past, it may look very familiar. And in fact, it mirrors the GeoJSON output format provided by our search API. So if you're using our search API, it should be a pretty painless transition. And in fact, in pursuit of that, we have the string serialization method produces GeoJSON that is actually identical to that of our search API. So in that case, it should be a drop-in replacement for users of the search API. And you can call on that simply by explicitly or implicitly casting the search results to a string. So here I'm just going to take my search results and wrap them in a print statement. And you can see I get some nice GeoJSON out of there, just as you would expect. It's a list of, I get to the bottom here, it's a feature collection of these feature objects within the GeoJSON spec. Additionally, individual ASF product objects can provide that GeoJSON-based serialization in the form of a GeoJSON feature snippet. You can see here, and that's just the individual features from above. I don't believe that's technically fully self-contained GeoJSON, but it can be used to construct GeoJSON as one might need. So in summary, for our basic usage, here is a complete example showing how simple a use of ASF Search can be. As you can see, we import ASF Search. Again, I like to rename it. And then we simply call asf.search with a couple search parameters. And because I want GeoJSON in this case, I wrap it in a print statement. And we give that just a sec to run. And there it is. So 2 lines, we can go from 0 to search results in hand. Next up, we will take a look at geographic searches. So previously, we were just doing a really basic search for a couple parameters, but usually we want to do something more interesting. And in this case, we will look at doing geographic searches using ASF Search's Geosearch function. This function accepts an area of interest in the form of a well-known text, as well as a number of other search parameters that you might want to use to refine your results. Again, before you start, we assume that ASF Search is available in your environment. And if you're following along at home, guidance on installing that is available at in the very first notebook. So performing a geographic search. We will start by looking at this in Vertex. Part of our goal here is to kind of help translate some of the typical Vertex workflows to ASF Search. So here I've done an ALOS Pulsar search with an area of interest over Kodiak Island in southern Alaska. You can see I have 44 scenes across 139 files. And we could pick through those and take a look at some of the results there. Say this looks good. Let's do this in ASF Search. Oh, also my date. My start date is January 1, 2010 through February 1st, 2010. So let's do that in ASF Search. Again, I simply import ASF Search, and I use a well-known text as my area of interest. And here I've previously copied and pasted that same well-known text that we just saw in Vertex. Save that to a variable. And then we assemble any additional search parameters, such as platform, date range, and the type of products we might be interested in. All options to Geosearch can be specified using keyword args, which allows them to also be handled using a dictionary. So here I will set up my dictionary of search parameters. In this case, platform, and I'm using the ALOS platform, using those convenient constants to make sure I get the name right. And then my start date is, as specified, 2010, January 1 through 2010, February 1st. And I've also set my timestamp on here to be midnight on the end, so I get the entirety of that last day. So once all our search parameters are ready, we can run the query and retrieve the results. And I do that by simply calling asf.geosearch. And in this case, I've said, I've specified my area of interest using the direct keyword arg, and then the rest of my arguments I've just added on using that ops argument. You could roll those together if you preferred. And then just for brevity's sake, we will print off the number of results we got. And if all works according to plan, we get the same 139 files found. So that looks good. And at this point, your search is complete, and you can use any of your usual workflows on your search results, such as spitting them out to GeoJSON and going from there. So a follow-on example, let's say we want to search based on a scene's footprint. So I've done that search above, and I found a scene in there that I like, and I want to use that scene's outline to do a subsequent search. So using Shapely, which is already installed by requirement of Asf Search itself, we can quickly produce a well-known text from a result and then perform a secondary search. So here I'm importing Shapely.geometry, or rather the shape class from Shapely.geometry, and I will set up a new AOI using my first result. So I grab that first result I had, I'll call the 0 index here on, and grab the geometry object. And Shapely knows how to handle this object, so it passes that in, and then we can create a shape object out of that, and then we can just grab the well-known text using that WKT method. So now my refined results will be asf.geosearch, and my intersects with parameter will be my new AOI, and I'll use the same ops I did before. And this is exactly why it's useful to be able to pass that dictionary of search options around, so you can reuse them. If we run that, we should see 279 results. So our search area actually, or our search results actually blew up a little bit. I think the area of that particular scene is larger than my original AOI. So let's trim it down a little bit instead. Suppose I want to search for similar scenes that overlap that scene's centroid. So the center point of that outline is my new area of interest, just the point. ASF provides a convenient centroid function. This returns a Shapely.point object for this purpose. We use this elsewhere, and it seemed sensible to expose this as a convenience instead of running all of this through Shapely manually. So similar to before, I'll grab that first result, and using the ASF product centroid method, I'll grab that centroid out. And since that is a Shapely object, I can again just call WKT on it and store that centroid as a well-known text. Next up, I will call asf.geosearch again, just as before, and feed it the intersects with keyword arg of centroid and the original ops arguments I had from before. And if we take a look at those, we'll just take a look at how many there are. We got 21 results. Okay, so we're narrowing things down. In summary, here's a complete example of using Geosearch. So again, import Asf Search and simply call asf.geosearch with a few parameters. Here's the same search we did before. That area of interest goes to intersects with, platform, start, end. And these, I guess it's worth pointing out, if you have used our search API, these arguments all mirror the arguments that the search API supports. So if you are trying to transition from that, you should be able to use all of the same keyword args. Run that. We can see in 2 lines, again, we have gone from 0 to GeoJSON search results. Pretty straightforward. Okay, next we will move on to Granule Searches. So Asf Search provides several search-oriented functions, and among those, next is the Granule Search. This function accepts a granule name or names, also known as a scene name, depending on which crowd you're talking to. And a similar function, Product Search, lets you search based on unique product IDs. So before you start, as always, Asf Search needs to be available on your system. So performing a Granule Search. Let's take a look at a Granule Search in Vertex. So here I have previously assembled a list of scenes I like. I have 20 files listed. These are over Sitka, Alaska, in Southeast Alaska. And you can see there's some nice images we have. So let's take a look at how to, I guess I can pull up the actual list. Here's the actual list of scenes I searched for. So let's see how we do that in Asf Search. As always, the first step is always make sure you have Asf Search imported. And then here I've just stored my list of scenes in a standard Python list. You can see they have all the usual components of those Sentinel-1 names. These are all Sentinel-1B granules in this case. I'll save those. Now, Granule Search does not make use of any other filters. So at this point, we are ready to go and we can run the search and get our results. So here I simply call asf.granule search and I provided that list directly. Take a look at the results. There they are. Again, I'm printing this so it's implicitly serializing to GeoJSON. For convenience, Granule Search also accepts keyword args as the other search functions do. So you can say Granule list is our Granule list variable and run that, and we should see the same number of results, those 20 products we found before. And then lastly, a single granule name is allowed with either of the above approaches as well. So if you forget to put this in a list because you have one item you're searching for and it just gets passed in, that will work just fine. And here you can see I found 2 results with that one granule, meaning that granule has 2 files attached to it. So performing a product search. This is similar to Granule Search. It's just a little more specific. Let's take a look at a product search in Vertex. And here I am looking at 4 specific products I found previously. And these are over the Des Moines, Iowa area. They have this kind of nice little layout here. So we have the product list here, and you can see in Vertex, I've pulled up the list search and I'm doing a file search this time. So these look similar to the scene names, except they have this additional file identifier at the end here. And the big key here is that these file names or these file IDs are specifically one-to-one. They refer to an exact single product. So if you put one in there, you will either get 0 or 1 result for a single product name. Useful for pinpointing specific items that you found and want to grab. So let's take a look at doing that in Asf Search. Here I'm importing Asf Search, and then I am storing that product list to a list here. I have my 4 items that we just viewed in Vertex. Save that. And then just like Granule Search, Product Search doesn't make use of any other search filters. So we have everything we need to run the search. And we do that by calling asf.productSearch and just dump that product list straight into the function. And we can look at the results. And there they are, nice and quick. Like Granule Search, Product Search also accepts keyword args for consistency with other functions. You can see there I'm calling the product search function with product list and our product list variable. I got my exact 4 results. And then if you, again, forget to wrap this in the list, it will just quietly work with what it's been given and find that specific item. So here we have 1 result found. A note on best practices. It's generally preferred to collapse a lot of small queries into fewer large queries. So if you have a long list of, say, 100 products or 100 granules, it may be easy and logical to run 100 different queries, just do a loop on that whole list. We ask that you don't do that. This makes a lot of resource usage at both ASF and at CMR. So it's much more preferable to combine those into a single large query feed your 100 items to a single Granule search or product search query, and then post-process the results locally. Granule Search and Product Search can support very large lists, and if needed, we actually break them up internally, so there's no actual hard upper bound on how long those lists can be. So very preferable to collapse those for better use of resources. This approach of using queries that yield all the desired results in one search call and then post-processing applies generally to all usage of ASF Search. So if you're using Geosearch functions and you're maybe breaking them up by days, doing a Geosearch query for each day, instead just grab the entire time range and then break it up locally. Be much more effective, and you'll find it's more performant too. So in conclusion on Granule and product searches, here is a complete basic example of using Granule Search. Again, I'm importing that library, Asf Search, and then just calling asf.granule search with, in this case, a single Granule name, and wrapping that into print to get the free GeoJSON serialization, and there it is. And then similarly, a identical example using product search, import Asf Search, and then call asf.product search with the list of scenes or list of products in question. Okay. That will take us next to baseline searches. So far we've looked at geographic searches and Granule and product searches. So baseline search is a approach for building baseline stacks, such as one might use for Insar work. We provide two primary approaches to creating a baseline stack. Before you start, always need to have Asf Search available on your system. And if you're following along at home, you can click that link and go through the instructions if you are joining us late. So building a stack from an ASF product. So say I have already done a search and I found some search results and I want to build some Insar stacks from those results. Let's start by taking a look at a stack in Vertex. So here I've used a reference scene, a Sentinel 1A reference scene. This happens to be over New York. And I'm looking at the baseline search type here. And we have, it looks like 170 scenes in this particular stack. You can see the baseline plot. We could switch to SBAS and do the short baseline version. So let's build this same stack in Asf Search. Excuse me. So I start by importing Asf Search, as always. Now, just as a bit of preamble here, I'm going to just do a product search. Again, we're building our stack from an ASF product, so that assumes I already have some search results in hand. So we'll build those real quick. I'm just going to do a search for a specific product, and then my reference scene will be the first, and in this case, only result from that particular search. So I'll run that, and you can see I print off my reference scene. This is an ASF product object, serialized to a GeoJSON snippet. So given those results, now we can simply call that product's stack method, and that internally looks at the scene or at the product, builds all the required parameters that are needed to build to create an effective stack, and then it performs a query based on those parameters, returning that stack in the form of another Asf Search results object. So we've kind of gone full circle. We've started with an Asf Search results object, and we've refined it, and then we've gotten a second identical object that details the particular stack we want to look at. So the way to do that, again, I have my reference scene here. This is an ASF product, and I will call the stack method. And we'll print off the number of items we got there, 171. So that lines up maybe, I forgot what the other one was, but we are constantly adding scenes to this archive. So if there's a discrepancy there, it's on my end. As stated, these results are standard Asf Search results objects containing a bunch of Asf products with all the usual functionality. So all the geometry and metadata and all of that stuff. There is one addition to the Asf product object in this case, and that is a new field in the properties dictionary. And if we take a look here, if we open that up, I'm just examining the properties attribute of the first item in our stack in this case. And that is the temporal baseline. This field is included when serializing to JSON. And you can see down here is the temporal baseline. And this is the number of days offset from the reference scene you specified. So in this case, this particular scene is about 2,500 days prior to the reference scene I used. I will note at this time, perpendicular baseline values are not available, but they are coming. We're working on that. So hopefully soon we'll have that available. It's been asked and it's pretty high up on our list. So building a stack from a product ID. So maybe I arrived at my particular product through some other method than Asf Search. I don't have search results to work with. I just have that product ID. In this case, I can make use of Asf Search's stack from ID method or function, I guess, to build a stack. So this simply takes a single product ID and builds up that stack and then returns as above the Asf Search results object. I'm using the same product ID as before, and I will simply run this, and we can see that we get, in just a moment, 171 products found in the stack. So that lines up perfectly. It's just a different way to get at that in case you don't already have search results on hand. Another note on best practices, this stack from ID function is provided as a convenience. Internally, it really just does a product search using that ID. So really just the same thing we did to build these search results in the first place, but we save you the trouble of having to go through the process of setting that up, and you can just call the function directly. For that reason, it is recommended that if you do have an ASF product object already on hand, use that. Saves you an extra search. It'll be a little faster. It'll be a little easier on us and the fine folks at CMR. So just a little best practice there. And for other cases where you have search parameters describing your reference scene, but not the actual ASF product itself, it's totally appropriate to just use one of the various search features available as needed. So in summary, on the baseline stacking functionality, again, we import Asf Search, we pick a reference scene, and then we call that reference scene's stack method right there. Run that. And we will get a rather large chunk of GeoJSON out describing all 170 scenes in that stack. And then the identical example using just the stack ID, if I don't already have search results on hand, we can run that and we should get identical GeoJSON. So again, 2 lines in this case to go from nothing to a full ASF or a full baseline stack to work with. All right, so next up, we're going to take a look at downloading data. This is a little longer section here. We have to deal with some authentication stuff. I mentioned that during the initial outline. So Asf Search provides a number of ways to find data, but of course, equally important is actually getting that data. It's fun to know it exists, but if you don't have it in hand, it's hard to do much. So Asf Search provides a simple interface through which to download data, and we provide a variety of authentication methods. So before you start, a little longer section here. We assume, of course, Asf Search is available. There's guidance for that. And additionally, this section expects that you have an Earth Data login account with the appropriate applications authorized, all the EULAs signed, the profile field set. There are a number of things there. Honestly, the easiest way to make sure that your EDL account is in order is to simply go to Vertex, sign in, and download a product. So there's a link here in the notebook to Earth Data Login. This takes me to my profile. You'll need to have yours set up, and then just try to download something through Vertex, and it'll walk you through any missing steps there. And then lastly, just for this notebook, we are going to assume a few directories exist, just a few download directories we'll use. You can create those, you can move them if you want, but I will just run this and that will create those directories in my working directory here on my system. So that'll make the rest of the examples later when we actually start pulling data work a little smoother. So because downloading any product in the ASF archive requires authentication, Asf Search provides this Asf session class. This is a subclass of session with a few specific methods added to make authentication straightforward. You can create, of course, a new unauthenticated session, and then you can call any of the various auth methods on that session. but we do allow for chaining for direct creation of an authenticated session. So we'll start by just making a blank session here. And again, I import Asf Search, and then I just call asf.asf session. So now we have this session object sitting around, but it is not authenticated, and we need to get it working. So the first option, of course, is to auth with credentials. And this just accepts a username and password and establishes an authenticated session with EDL, that's Earth Data Login, and ASF, our data pool systems. So for the example here, I'm going to use a couple functions just to get the information we need. I'm going to grab my username and then my password. And here you can see I will then attempt to call asf.asfsession.auth with creds. And I feed it that, here we go. Couldn't scroll over. I feed it that username and password, and then it will attempt to run the authentication process. It will throw an exception if something goes wrong. So we will run this, and I'll punch in my EDL username, and just for demonstration, I'll put in definitely not the right password. And you can see it says auth failed, username or password is incorrect, and that's that exception right there. So let's run this again and do it right this time. And so this reaches out to EDL, establishes a session there, and then gets redirected over to our services and establishes the full session there. And you can see it's been successful. This is all ready to go now. We could use this session to download data. Another approach is to auth with token. So this authentication method accepts an Earth Data Login token, and then that's included as part of an authorization bearer header on any downloads that make use of that session. So to generate an EDL token, there's a link here. You can go to your Earth Data profile, and at the kind of the top of these little tabs here, you can go to generate token, and you just click that green button there to say generate token, and you can then copy it. I've copied mine. Now that is considered a secret, so don't go sharing that around. It's nice that they actually provide this copy thing that we can do this live here. So now I have a token, it's in my clipboard, and we can run this approach. So I will again use the get pass function just to grab my secret token here. So it'll ask for that, and I'll paste that in. And once that's done, then it will establish, I call asf.asfsession.auth with token, and I pass that token in, and it will establish an authenticated session. Now, this is super convenient. Honestly, my favorite approach, but it is worth noting that not all data pool hosts are compatible with this authentication method yet. We're working on it, we're getting there, but it is fairly new functionality with EDL, so it is not completely available everywhere. So if you do have problems using this approach, probably fall back to the user and pass option. So lastly, we have auth with cookie jar. This method accepts an http.cookiejar compatible object, such as a previously authenticated session stored for use or stored for later reuse. For this demonstration, we're just going to grab one of our sessions from above. So I'm going to grab the cookies from our user pass session. Then it's assumed that I've taken that cookie jar object and saved it to a file, loaded it later, etc. Whatever I may need to do with it in the meantime. At that time, you can create a new ASF session using that cookie jar. And of course, while it's not required to use the ASF session class to do this, we provide this approach just for consistency's sake, just so you can always be using ASF session and have the expected behaviors there. So to do that, we simply call asf.asfsession, and we can chain that auth with cookie jar method and pass the cookie jar that we grabbed and saved and reloaded. So now we have a cookie jar session that is also active. So at long last, downloading actual data. Let's take a look. We have a Geosearch here we're going to use as an example. Let's take a look at that in Vertex. So here I am looking at some UAV SAR data over the southern US around the coast of Louisiana. Really neat UAV SAR data down there. I love some of this stuff. It's gorgeous. So we have the data set is UAV SAR, the Polygon, or our area of interest is this Polygon. And we're not using any other filters except that I have set the file type to metadata. And these are just these wee little annotation files. They're under 30K. We're going to use those for our download examples because I can download a lot of them really fast. So our search results are restricted to that. So we've already handled the authentication above. So we can start downloading these products. We have, again, we just looked at that search in Vertex. We have our area of interest here in the intersects with parameter. Our platform, we have asf.platform.uavsar. And our processing level is set to asf.producttype.metadata. A little bit of an overloaded term there. But again, making use of those constants so that I don't have to remember what that value actually is. And then we're going to limit it to 250 results. So let's take a look at what we get. This should say 250 results found. Looks good. And we know that because we limited it to that metadata type, they're all going to be those annotation files in this case. In reality, you would probably be downloading the actual products. So to download a single ASF product, we simply call its download method. We pass in a previously authenticated session, a path at which to store the file, and optionally a file name. If you don't give it a file name, it will default to the actual file name of the product itself, as described in the file name property of the ASF product object. So we will take a look at the first search result we had. We ran that search above. We got 250 results, and we're going to grab the first one, and we just call .download. So this first result is an ASF product object. We call download, and we pass it our first download directory. In this case, downloads1. And then we tell it the session is we're going to use our user pass authenticated session. So if we run that, it will download. And then here's just a listing of that directory, that downloads1 directory. And you can see there's our annotation file, just like that. More often than not, though, we want to download a bunch of products. And so ASF search results, the list or the user list class for these things, provides this functionality similarly to ASF product via the identically named download method, but with two key differences. And that's that the file names always use the default behavior. So as if you called the products download method, but with no file name. And then that downloads can occur in parallel. So we can download a bunch of things all at once. If a particular file already exists, a user warning will be emitted, but that file will just be skipped. It won't halt the actual process. So next, I'm going to download, to demonstrate that, the first 10 results from our search results. I'm going to save them to that same downloads directory and give it the user pass session for authentication. Now, I mentioned that it'll spit out a warning if a file already exists. We have already downloaded that first result, so we're going to try to download it again as part of this, and we'll see what happens with that. So here you can see it's a user warning. Says file already exists, skipping download, and then we carry on. And once it finishes downloading, we list out the directory, and you can see there are our 10 files that we requested. So the above example downloads each file in sequence by default. I did mention that we support downloading in parallel, and it's often much more performant to work that way. So with that in mind, the ASF search results class's download method allows setting a maximum number of downloads to run in parallel. And you do this simply by setting the processes argument when you call that download function. So here I'm going to download them all to the downloads2 directory and feed it that user and password authenticated session, and then tell it 50 processes. Now this is super aggressive. I know that I'm downloading these tiny files. They're 30K. It's fine. If you're downloading, 8 gigabyte SLCs, you probably don't want to run with 50 in parallel unless you're on a really beefy connection. So we're going to save that to downloads2, and just for fun, as we go, I have my working directory here. Here's my downloads2 folder, and we're going to watch those come in because they will come in fast. It's pretty exciting. If you've ever downloaded our data before, getting stuff quickly and in parallel is hassle. So this really simplifies that process. So I started that code, I've switched, and already I've got 100, 150, 200, and I believe it's probably done by now. The Finder is actually slow to catch up. maybe it's going just a touch slow. Okay, so there we go. We just downloaded 250 files in just a matter of a few seconds with all of one line of code. Pretty handy. Lastly, downloading arbitrary URLs. So it may occur that you have a list of products that you want to download, but you've not arrived at that through Asf Search. Maybe you have a service in the cloud and it's convenient to just copy and paste a list of URLs in. Maybe a colleague sent you a really exciting spreadsheet full of product URLs. In that case, Asf Search does expose its download functionality more directly through the download URLs function. Takes a list of arbitrary URLs, a path at which to save them, and an authenticated session, and optionally a number of downloads to run in parallel. So in this case, I have a list of URLs I've just grabbed from some previous search results. Again, these are all UAVSAR metadata files, so they'll be small. And then I call that asf.downloadURLs function, passing in the URLs, the path, and the authenticated session. And in this case, I'm grabbing 5 files. They're small. I know it's going to be easy. I'm going to run 5 in parallel. So we can run that. And just a few seconds later, it has grabbed all 5 of those files, and those are now stored locally. So a complete basic example of downloading search results. We can take a look at this. Again, I'm going to use my username and password to start from 0 and build up a session. So I import Asf Search as ASF. I call asf.asfsession.auth with creds, and I feed it my credentials that I've collected up at the top here. I will do a Geosearch to find some data. I'm going to use an AOI, well-known text string here, and I will do my search for the UAVSAR platform using those constants. I will limit it to my metadata files for efficiency in this example, again using those constants, and I'll just set it to 20 results tops. And then I immediately call results.download. The path, I'm going to save it to my downloads folder. The session that we built above, I'll pass that in, and I will run 10 in parallel here. So run that. It'll ask for my password. I can put that password in, hopefully correctly. And so this immediately goes out, takes a moment to build the session. It has to talk to a couple different services for that. Takes a moment to run the search. And get those results back. And then once that's done, it can actually go and download the files. And it was faster than I could even describe the process. So pretty simple and efficient to use. All right. Well, that kind of sums it up. Thank you all for listening. And a few tips on where to go next. Again, Asf Search is available through PyPy, Conda, and GitHub. You can just search for Asf Search there on PyPy and Conda. The notebooks used for this presentation are all in the GitHub repository. If we take a look at that, it's in the examples directory right there. And again, this whole thing is open source and freely available. If you want to submit issues or have questions or fork it yourself or even submit changes, we are happy to have you involved. If you want to contact ASF, we have links in the notebooks for the ASF website and some direct contact form. And I really want to sell this a little bit. You can contact the ASF Discovery Team directly through Gitter. If you've not used Gitter before, it's a GitHub integrated messaging platform. There's a link here in the notebook. It's also on the repository, and you can see we have a few groups here. We have the community group for ASF Discovery, as well as some rooms specific to Asf Search and some others. Lastly, I'd like to say thanks to the ASF Discovery Team. It's Andy Anderson, Tyler Chase, Alina Ellis, Kim Fairbanks, Christy Fleming, myself, Cameron Showalter, and William Horn. And extra thanks to Christy for reviewing all these notebooks for this presentation today. And a huge thanks to Jennifer for making this all possible.
A comment that I know you wanted to address first, and that had to do with, can you please suggest a cloud platform for Insar processing?
Yeah, so this, I saw this before the talk, and it really got me excited. Through Vertex and more importantly, the Hype team at ASF, the tools team, we provide on-demand custom processing in the cloud that is free of charge. There are some limitations on it, but I would strongly suggest you swing by our website and take a look there for the the on-demand options there. And it looks like Joseph Kennedy has actually posted a link to the docs about using the SDK for Hype. And we also interact with that through Vertex. So depending on if you want to do it programmatically or through a GUI, there are options there. So that is absolutely a great place to look for Insar processing in the cloud.
Okay, great. And so the next question is, can this same API be used to fetch Sentinel-2 and Sentinel-3 or other Sentinel products?
Not at this time. So ultimately, this library is focused on ASF data. As that data becomes part of the ASF catalog, of course, we would include it there, but it is limited in that way. Now, that's not to say that you couldn't grab the thing and fork it and point it at whatever data you might like, or that our archive will change in ways that we would be able to support that in the future. So it could be, but at this time, no.
Okay, thank you. And so one of the questions that was asked really early on, is it possible to have an example where oil can be detected in the sea? And this might be something where you need to follow up offline.
Yeah, that would be more a question for some of our in-house scientists. Absolutely reach out using that contact link on the ASF website and
fair enough.
Make touch with us there. That
Perfect. Way. The next question is, why is the product type showing a polygon? It's a raster image, correct?
The polygon there is the outline, the footprint of it on the actual dirt, approximately. So yes, it is raster data. That is just descriptive of the extent of that data.
Okay, thank you. Can Asf Search be run on the Google Collab platform?
I'm not super familiar with that platform, honestly, but anywhere you can run Python, you ought to be able to run Asf Search. In some contexts, you might run into issues using the parallel download functionality. I know in the interactive interpreter in Python, it sometimes throws a fit if you try to download stuff in parallel. But really anywhere you run Python.
Okay, great. Thank you. The next question is, what is the availability of these images both geographically and temporally?
That really depends on the data set. We have some data sets going back decades. We have more recent data sets like Sentinel-1 is ongoing since, 2000 mid-teens. I don't remember the exact dates. And other data sets like UAVSAR are ongoing. It really depends on the data set.
Okay. Thank you very much. The next question is, can the search results be reprojected? For instance, if my area of interest is not in the UTM WG S84, can I still intersect with Asf Search directly, or will I have to do it externally?
Oh, that's kind of a big question. Ultimately, we're working in latitude, longitude AOIs through that well-known text functionality. If you need to do more complicated approaches than that, it would fall to you still to get the area of interest that you're working in within that system.
Okay, thank you, Greg. The next question is, do you have any plans to make a webinar or training in Insar processing with Python for Subsidence?
I don't. I would direct you to our tools team. They are active in the chat here, it looks like. They have some scientists on board that could certainly speak more sensibly to specific applications of the data.
Okay, wonderful. Thank you so much. Can we use this API to download data from Sentinel Hub?
Perhaps. That's kind of a fun one. And that might be one that you should hop on Gitter and chat with us about. We do have that generic download URLs function, and you can pass in a session. So you may have to build the authenticated session yourself and do some lifting there, but then you would still be able to use the generic download functionality, I think, with anything. So far as I know, you could feed in a list of Google image search URLs and download stuff using that.
Okay, thank you, Greg. Let's move on to the next question. Okay, can we geocode the data and subsequently subset the IW data before download?
I'm not sure how best to answer this. Well, I guess Joe's jumped in and said no. That's probably the most succinct answer. You can certainly subset all your search results, but we aren't actually working with data in the ASF search space. This is all about finding the products and scenes and getting access to them, not actually manipulating the raster data itself.
Okay, thank you, Greg. The next question is, the UAV SAR image we download, can they be processed through Pulsar Pro and perform decomposition and other analysis?
I'm absolutely going to let the tools team handle that one. Yeah, again, we're not in the actual data manipulation space here. We're in the discovery and acquisition space. So if you need to follow up offline with some more data-oriented people at ASF, we can certainly help you get in contact with the right folks there.
Yes, and you can always submit a ticket to support@earthdata.nasa.gov, and that will be routed to the ASF DAAC as well. So that's another option for reaching out. The next question is, does the API support the on-demand Insar data? And I think we kind of addressed that a little bit.
Yeah, so ASF Search doesn't do anything with that, but you can certainly take any results you build with ASF Search and use them in conjunction with the Hype SDK that is available to do on-demand processing that way. So it's kind of, they complement each other.
Okay, thank you, Greg. The next question is it possible to download a stack of co-registered images?
You can download the stack. Co-registration I cannot speak to, unfortunately. We'd have to follow up with that online with some subject matter experts. All
right, thanks again. So the next is more of a comment than a question, but the comment is, it would be very beneficial to integrate today's ASF search into the ASF SAR MOOC on EDX. I am an ex-student of that great course. So that's a suggestion there to pass.
Great. I mean, we love feedback like that. Absolutely.
Perfect. The next question is it possible to process a bunch of raster and ROI with many conditions from different sources? Sentinel 1, I think this is right, S1, S2, UAV data, etc., with ASF Python library.
Yeah, so that's well outside the scope of what I'm able to answer here. And I'd say we need to follow up on that offline.
That sounds great. Thank you. Is it possible to download sub-Swath data?
We aren't doing any sort of subsetting through ASF Search. You would have to download the entire product and then do any processing workflows after.
Okay. Okay, thank you, Greg. The next question is there any delay regarding data availability on ESA, Sci-Hub, and ASF?
I mean, there is a turnaround from it until we get the data. It varies. I don't know what it usually is, maybe a few days to a week. It doesn't show up immediately, but it's pretty darn quick. And if you watch the archive, actually, you can see it just constantly data is flowing in. And it's just a little delayed.
Okay, wonderful. Thank you so much, Greg. Let's see here. Check back to the chat. Is there any way to analyze and process SAR data in Python, like radiometric calibration, speckle filtering, terrain correction, and so on? So we actually, I don't know that we have held several webinars which touched upon processing data in Python, and I could certainly put the 2 links in the pod, but I'll let you address that as well.
Well, and Joe has posted a link to our Hype docs. That's a good place to start. They provide some cloud-based services, but you may be able to work forward from that if you wanted to do things more locally, or just reach out to the tools team there and engage them. They would have some better suggestions on actually working with the data.
Okay, thank you very much. So I think at this point, what we'll do, I'm just looking to see if there are any other questions. Just as a reminder to everybody, today's webinar was recorded. We will post it both to the YouTube channel, which is www.youtube.com/c/earthdata, NASA Earth Data, and we will also post it to the webinars and tutorials page within the NASA Earth Data website. And so I have placed those links in the chat a few times, but I will do so again. What we will do is log off from the audio component, and I will see if I can figure out these end polls, but otherwise I'll follow up with a Google form with the final 3 questions. Thank you, Joseph, too, by the way, for entering the link into the chat. That's very helpful. So I am not seeing anything else. Yes, I will place the Jupyter Notebook link into the Q&A again so that everybody, if you joined a little bit late, you'll be able to access that. So at this point, we will log off from the audio component of today's webinar. If you have a few minutes to stick around while I see if I can get the final polls up, that would be wonderful. So thank you, everybody. Thanks to our speaker, and thanks also to the team at ASF who logged in and has provided some helpful information in the chat. And with that, we will see you at an upcoming webinar. So thanks so much, everybody.